Okay. Ready for the next ride? So 20 minutes. I'm going to apply all the procedure here. I outline here. First, I elevate our equation into a complex version, and then I plug in a guess, which is a exponential function of complex variable, 复数的指数函数. And then with this guess, all the derivative becomes the power of alpha. Second derivative is alpha squared. And then the differential equation now becomes an algebraic equation. And you can solve alpha easily. For in this case, alpha is just equal to plus and minus I alpha. Plus or minus I omega. And the solution I can write down right away. It is Z0, a constant, complex constant, times e to the plus or minus I omega t. Okay, now let's take Z plus for example. If you take the real part of this Z plus, it becomes the solution we are familiar with. Okay, and use this real part, we can form a solution which satisfies both the ODE and the initial condition, the same story again and again. Then this is the unique solution. You may raise your hand. Professor, you say that imaginary part of Z plus is also a solution. Where are they? Where is it? And also there's Z minus. So how about the imaginary part of Z plus? So let's take a look at the imaginary part of Z plus. You can see that the imaginary part of Z plus is A times sine omega t plus phi. But you can easily write it in terms of cosine because sine omega t plus phi is equal to cosine omega t minus 90 degree or pi over 2. Check yourself. Okay, so it is equivalent to what we have already got. Okay, so of course the imaginary part of Z plus could be also a solution, but we don't have anything new. It's the same equivalent to what we have already have. The same story applies to Z minus. Sorry, this is so the imaginary part of Z plus is equivalent to the real part of Z plus. And then you can check Z minus. Z minus also has a real part and imaginary part. I think this is the real part, so here is the minus. This is the imaginary part minus omega. But you can, again, easily demonstrate that this real part is equal to A cosine omega t minus phi. Okay, so it is of the same form as what we have already had. Just replacing this plus phi by minus phi. But phi is just an unspecified constant. Okay, whatever way you write it, they are equivalent. Okay, so again, we don't have any new solution. The same thing applies to imaginary part. You can check it here. So that means we got only one set of independent solution from the real part of Z plus, and that's good enough. That's good enough. That's enough, again, for us to satisfy the equation and also satisfy the initial condition, and that's unique. Okay. Now, any question? If not, let's ride a roller coaster. 20 minutes, maybe 15 minutes now, we can get everything done. First, simple damp oscillation. I don't need to introduction here. The damp oscillation, the original equation of motion, x dt squared, because there's damping, so we add a dx dt term. So plus b over m, of course, remember b is the coefficient signifying the proportional constant of the damping force. B over m dx dt plus omega squared times x equal to 0. First step, elevate it into a complex version. So x becomes z. Because it will be so fast that you better raise your hand if you miss something, or I miss something. So d squared z dt squared plus b over m dz dt plus omega squared z equal to 0. Now it's z, not x. Z is complex number. And of course, this is all the same argument, so I don't want to repeat again. The real part, the imaginary part of z, both satisfy the same equation of motion. So if I got z, I got real part. Take a real part, I got the solution of the original equation. So, a brave guess, but it's a guess I did already. Exponential omega t times z0. Plug it in, every term is proportional to z. Second derivative, alpha squared. First derivative, alpha. No derivative, then the z again. So we got alpha squared z plus b over m alpha z plus omega squared z. Z could be cancelled out because it's the same thing. It's a function. It couldn't be 0, so I can cancel out z and arrive right away. Ladies and gentlemen, alpha squared plus b over m alpha plus omega squared is an algebraic equation. The same story, the second time. So from a differential equation, by this genius invention, genius guess, Trump's guess, then we arrived at the equation algebraically. And it, of course, could be solved. It's a high school student, high school mathematics problem, right? 我们从大学回到了高中啊，高中才在解这种二次方程式嘛，不是吗？哦，好，所以 everybody knows the answer for alpha. Alpha is equal to minus b over m plus or minus I square root of omega squared minus b over 2m squared. You check it yourself. The solution for this second order equation is equal to this. Let's call it alpha plus and alpha minus depending on the sign of this term in front of I. Okay? And if omega squared is larger than this, of course, that means I will later check the case if this is smaller than this, but that's later. If alpha squared is larger than this, that means the b is not too large, then this term is positive. It's positive. So let's call it omega prime. Omega prime is defined as the square root of omega squared minus b squared over 4m squared. So the solution alpha now has a real part. The solution alpha now has an imaginary part. Ladies and gentlemen, when you have an imaginary part and also a real part, then that means the solution will be the product of an exponential function and a trig function. I told you already, right? Okay, so put it together. This solution, z plus or z minus, both. Z is equal to z0 times e to the alpha plus or minus t. And because alpha plus or minus has a real part, has an imaginary part, I better separate them into each other, separate them into two terms, sorry. So it becomes e to the minus b over 2mt. This is the real part. Exponential plus or minus I omega prime t. So everybody should recognize the second term will be cosine and sine. And the first term will be exponential. That's what I say. This solution is a product of an exponential function times a trig function, oscillating function. We are done. Remember, the week before last week, I say that I am not going to solve the equation because I'm going to solve it in the future by a systematic way. Now, ladies and gentlemen, there you go. I solve it in a systematic way. So, this is a decaying amplitude. This is oscillation, of course, the real part. But only the real part matters in our solution, right? So we pick the real part of complex solution z plus. We arrive at x equal to a times exponential minus b over 2mt cosine omega prime t plus phi. The real part. And the real part has two unspecified constants, a and phi. and we can use them to fit the initial condition. After that, then the solution will be the unique solution of our question. Well done. You can see that I copy the two transparency from earlier. Almost the terminology are the same. That signify it's not because I'm lazy. It's because the procedure is exactly the same for simple harmonic motion and for damped oscillation. The procedure is exactly the same, so you can compare the two photographs, the PowerPoint page. They are exactly the same. Okay, so the solution I arrive at is the solution of a damped oscillation. Remember, that's the original PowerPoint page. When we talk about damped oscillation, I told you that it's oscillating and the amplitude will decay, da 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 da. Now, at that time, I told you that I'm not going to tell you how to solve it. Now, I have already told you how to solve it in a systematic way. And also at that time, I mentioned if the damping force is too large enough such that omega is smaller than b over 2m, then there is no omega prime. Because this omega prime is negative. Sorry, omega prime square is negative. Therefore, if this is negative, then there's an I, and the double I becomes -1. So in another way, in order to say it, alpha plus and alpha minus now are all real, not complex number. Could you get that? 假如你的这个阻力太大的时候，这个根号里面的这个东西根本是负号，开根号呢就有一个 I， 那一个 I 碰到一个 I 就没有 I 了，because I squared is equal to -1. Okay, so that means when you in this kind of case, the alpha, the solution are not complex. The solution are real. Okay, it could be written as, check yourself, you could be written as minus b over 2m plus or minus square root of b over 2m squared minus omega squared, because I reverse the two sides. Okay, and get an I, and that I multiplied by the original I give you a minus a plus sign. It doesn't matter. You can flip the two. Okay. The key is, written this way, we find that the two solutions for alpha are both real. If they are both real, that means there are two exponential functions, no oscillation. Remind you the last time, if there is a real part of alpha, it's exponential function. If there is imaginary part for alpha, then it's oscillating. So no imaginary part, so no oscillation. So when the damping is too large, no oscillation. You have the X, no oscillation. So it's damping up or damping down. That means exponential rising or exponential increase. If it's exponential rising, then there's a problem, right? The solution could not be increasing by itself. But no, look at the solution. It's b over 2m minus this, and b over 2m plus this. And if it's plus, then this is positive, this is positive, the whole thing is positive, so exponential decline. This minus this, you have to make sure this is larger than this. Of course, it is, because the second term is b over 2m squared minus omega squared. Omega is positive thing, right? Okay, so this square root is smaller than b over 2m. If this is smaller than b over 2m, then inside the parenthesis it's positive. So again, exponential decline. So both solutions are declining, exponentially declining function. That's it. Oh, both of them are decay function. Just like what I write down here. Okay, so of course you may ask, now how about if omega is just equal to b over 2m? Oh, okay, it's called undamping. It's over damping, it's under damping. If it's undamping, well, it's really hard to say how to adjust your apparatus to reach undamping, but mathematics. So it's not physical solution. It's not a physical solution. It's impossible to really adjust the apparatus to just so that omega is equal to b over 2m. Physically, it's impossible. But mathematically, they will ask, how about if this is true? I'll give you the answer next week. Because we are going to use another method to solve this question. But anyway, it's a mathematical question, not a physical question, so I'll just forget about that. 这是个物理问题啦，不是一个物理问题啊。因为呢，你要刚好 omega 等于2b over 2m， 你要把它仪器调到刚刚好才行啊。那物理的仪器没有那种调到刚刚好这回事，它一定有一些误差。Okay, so it couldn't be undamping. It is either over damping or under damping， 没有刚刚好。但是数学上它可以问啊 ，for mathematician he can ask what happened in this case。OK， 好，所以下礼拜告诉你 ，we're going to use another powerful method。那个不会在考试的范围里头，但是呢，下礼拜告诉你这要怎么算。你有兴趣可以先看，用一个方程式。OK， 好 ，OK， so I hope I used 10 minutes. I hope everybody agree with me that the above solution could be systematically generalized to any differential equation with constant coefficients to arbitrary order. Okay, you simply need to again elevate the x into complex and get a solution like this. When you plug in, a differential equation now becomes an algebraic equation for alpha, and then you can solve alpha. Usually, for algebraic equation of order n, they have n solution. Okay, if they have n solution, you can just form linear combination to get a general solution, and then pick the real part. It's the same procedure. Okay, so ladies and gentlemen, I finished telling you how to solve linear differential equation with constant coefficients to arbitrary order. Even though we only encounter n equal to 1 decay equation, n equal to 2 simple harmonic motion, but the same method could be applied to anything, to be any order. Isn't that powerful? You may ask, could the same method be applied to inhomogeneous solution, inhomogeneous version of simple harmonic motion, the so-called forced oscillation? The answer is yes. Okay, but usually it is easier if this force, external force, is a cosine function. For example, in the formulation I gave you, the right-hand side is written as f0 over m times cosine omega dt. Remember, I remind you that this omega d is not the same as omega. This omega d is the frequency of the external force. Okay, that's a separate parameter I can adjust in additional to the omega. So now, could I do the same by elevate the real x into a complex number function? The right-hand side is easy. You simply need to replace x by z, x by z, x by z. How about the right-hand side? Take a guess. The right-hand side is cosine omega dt. If I want to elevate it into a complex version, let me give you a recipe. The recipe is you replace it by exponential I omega dt. Why? The reason is pretty simple. Because the original source term is the real part of this complex version of the source. So when you take the real part of this real complex version of equation, the left-hand side becomes x, the left-hand side becomes x, the left-hand side becomes x, the right-hand side recover into cosine. That's the only trick. the only trick. So let me put it in Chinese. OK， 右手边呢是一个 cosine 的 function。OK， 所以呢你要把它变成是复数版的时候，你要有一个 trick。这个 trick 呢，就是你不是直接把它写成 cosine， 而是你要把它写成 exponential 的 I omega dt。这样写的原因很简单，因为这个家伙它的实数部就是原来的 cosine 的 source term 嘛。对，我讲太快，你要举手啊。好，所以对吧 ？OK， 所以我如果我的这个复数版本的右手边是一个 exponential I omega dt 的话，那么这一个复数版，我全部取实数部的时候，这一项变成是 real z， 这一项变成 real z， 这一项变成 real z， 这一项变成 cosine omega dt， 就回复 recover 到原来的 source term。但很明显的，你就可以看得出来，这个方程式就是原来的方程式，被谁所满足？被 real z 所满足。So the claim is this: if I can solve this equation for z, a complex solution, take the real part, I got x for the original inhomogeneous equation. I'm almost done. So the key is to solve this. Now take the same guess, z0 exponential alpha t. Put it in. Second derivative means alpha squared. I go fast, roller coaster. So first derivative means alpha. No derivative means no alpha. So the left-hand side becomes alpha squared plus b over m alpha plus omega squared times z itself. Okay, it's the same calculation as the one I have given already. Now we add a second, the right-hand side. It is exponential I omega d. So now the equation equates this with this. So it's obvious. Alpha now has only one solution. You compare the left-hand side and the right-hand side as a function of t. The only hope they are equal is alpha equal to I omega d. So the solution is quite different from earlier. In homogeneous, the solution using the same procedure, we arrive at one solution. This one solution, the frequency alpha, is equal to the external source frequency. I hope you still remember when I talk about force oscillation. When I arrive at the resonance solution, I told you that it oscillates with the external force. Now it's here. Alpha equal to I omega d instead of omega. So alpha has only one solution, which is I omega d. So if alpha has only one solution, then z0 has just one solution. In the homogeneous version, the z0 is the solution with two unspecified constants, right? A, phi, we use to fit the initial condition. But here, this z0 could not be arbitrary. Again, very, very different from our derivation just 5 minutes ago. Here, z0 has only option, which is equal to f0 over m divided by this more or less complex number. Because you can see that if alpha has only this solution, so this equal to this equal to this, so we cancel out, and z0 will be equal to this divided by the whole, and the alpha, we plug in alpha equal to I omega d. So the term in the parentheses will be written in this way, and take it to the right-hand side, we solve z0. So we're done. We got one solution. This is a so-called resonance solution. Okay, it may not be very obvious to you why this is the resonance solution. Okay, so I urge you to go home during your spring break to check. It will appear in one of our problem set today, that you can check this z0 can again be written in terms of its absolute value and a phase angle. But instead of two unspecified constants a and phi, now a has a specific value, phi has a specific value. Okay, a is equal to this. The only thing you need to do is to do the calculation. 有理化，我不知道英文怎么讲。有理化呢，这个那个复数，把它变成下面是实数，上面的是复数。经过一些计算，你就可以得到它的绝对值是这个结果。它的 phi 是这个结果。Again, let me emphasize, in these two expressions, nothing are unspecified. Everything is specified. 所有东西都是确定的。所以 we are talking about one solution. Okay, we are talking about one solution. That solution equals to a times exponential minus I omega dt plus phi. But instead of phi and a as unspecified constant, now a is this, phi is this. They are both specified. And if you look at and take a real part, the solution will be a cosine omega dt plus phi. This you can check with my earlier transparency, my earlier presentation. This is exactly the resonance solution. A is the amplitude. Oh, I forgot. I didn't write this. Okay, XR. Remember? Just make a diagram. 好，所以你回家自己可能要做一下。familiar with yourself with some of the tricks in complex analysis. Try to find why this A is equal to this expression and tangent phi is equal to this expression. If z0 could be written in this way, okay, and you need some mathematical manipulation to arrive at this result. So resonance solution. 所以各位同学，我们在前面上一个礼拜讲的里面没有教你们的，现在全部都补上去了。Damp oscillation 的解没有解，刚刚修了。Resonance oscillation 也没有解，现在都解给你看。OK， 所以呢，考试考到今天这里，所以呢，the exam will cover until this point, or until this point. Some of the example will be given in the problem set 2. Problem set 2, you don't need to hand in problem set 2. But I urge you to do the exercise during the spring break so that you are familiar with more or less these materials. Okay, and we'll see you again next Thursday, and then on April 13th we'll have the examination. It will be simple. Don't worry. Okay, it's your first course in mathematical physics. I don't want to frighten you. Okay, so it will be very, very simple. Just follow the problem set. Follow the. I will also give you a preparation PowerPoint so that you can concentrate on the things I will have problems. OK， 好吗？那我们就祝大家有一个快乐的春假，一定是不快乐的啦，我晓得。You won't be happy with the exam looming in 2 weeks, but what can we do? So happy spring break. See you when you are back.